Today we're going to continue our discussion of statistics and standardized testing, and we're going to talk about correlations and regression. So correlations and regressions are measures of relationships. So we typically use this in standardized testing when we're talking about how measures on one assessment compare to another. And the first thing we do is graph it on a scatter plot. So we are looking at the relationship between x and y. So you can see x and y. So we're looking at the relationship in this graph of SAT scores, so verbal scores to math scores. So what can you see on this graph? We can see that as students' verbal scores on the SAT increase, we see that the math scores also tend to increase. So as we're looking at scores on tests, now we're looking at per capita income versus AYP failure. So that would be adequate yearly progress. So students who are not passing the state test. And now we can see we have the scatter plot of per capita income and failure rates, but we're also, now we've drawn a line through that. So what we can do is we can have a computer program draw a line of best fit through that data. And as we do that, when we draw that line, we are looking at that correlation coefficient, which measures the direction and the strength of the relationship between these two variables. And it ranges from -1 to 0. And that line is the end, the slope. The correlation coefficient is the slope of that line. Remember that from algebra. So y equals mx plus b, where y and x, b is the intercept, and m is the slope, the rise over the run, right? So that m can range from -1 to 1, and it tells us the direction. That would be if it's positive or negative, and the strength, that would give us, how steep the line is. So that tells us if the relationship between income and failure is positive or negative. And we can see here it's negative, right? So the greater the income of a student, the fewer failures there are on AYP. And this strength, right, that tells us how much of the relationship it is. And we can see it's a pretty strong relationship here between income and failure rates. But the important thing to note here is that correlation does not imply causation. So it's not that being poor causes you to fail. It's that all of the or that we don't know that. This data doesn't tell us that being poor causes you to fail. All it tells us is that those two things are associated. If we wanted to prove that being poor causes you to fail, what we'd have to do is assign some kids to be poor and other kids not to be poor, and then see how that affects their failure rates, which wouldn't really be ethical, right? But the important thing to know here throughout this entire lecture, and we're going to say this over and over again, correlation does not imply causation. So let's look at some other examples, and this is really going to underscore this idea that correlation doesn't imply causation. So if you have a big enough data set, you can find lots of spurious correlations. So for example, the divorce rate in Maine correlates with the per capita consumption of margarine in the United States. Let's see. And the number of people who are electrocuted by power lines correlates with the marriage rate in Alabama. The worldwide non-commercial space launches correlates with sociology doctorates awarded in the United States. So here's a funny comic. It says, I used to think that correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. So now we're going to talk about regression analyses. And the cool thing about regression analyses is that it allows us to put a lot of things into a correlation analysis. So in correlations, we were only looking at 2 variables. In a regression, we're going to be able to look at a lot more variables in one place. And all those other factors we're going to call covariates. So let's look at a quick example here. So let's look at the relationship between school achievement and exercise. So it turns out that there's a pretty good relationship between school achievement and exercise. The more you exercise, the higher your school achievement. And all of our PE teachers out there would love to say, well, look, great, the more kids exercise, the more they're going to achieve. But we're forgetting some other really important variables. When we include gender and socioeconomic status, the relationship changes. Why would socioeconomic status affect that relationship? Let's think about it for a second. Right? So who's getting more exercise, right? Kids who are on dance, kids who are on soccer teams, kids who live in safe neighborhoods where it's safe to go outside and play in their backyards and on the street, right? So kids from higher socioeconomic statuses are able to get more exercise, right? And we saw from before, kids from higher socioeconomic statuses also have higher levels of achievement. So the relationship between school achievement and exercise is partially at least explained by socioeconomic status. So it's not fair to say that school achievement and exercise are related without accounting for other variables like socioeconomic status. That's why regression becomes really, really important. So again, we want to be thinking about all of these areas, and this is going to ruin the news for you forever, right? So when they say things like, well, drinking more red wine will help you live longer. Well, think about it. Who could afford more red wine, right? People who make more money. We also know that people who make more money also live longer because they can afford things like, health insurance, right? So it's really important that when we see these correlations reported in the news or when we see them reported in educational findings, that we're really thinking about all of the other factors as well, right? So here's some pitfalls to regression. So while regression's amazing and it can do lots of really cool things for our statistics and our analysis and research, we want to think about what are some problems with it. So one problem would be using regression to analyze a nonlinear relationship. So let's look at this graph over here on the left. If I ask the computer to, it will draw a line of best fit through these data, right? It'll draw a straight line through here. What's the problem with that? Is that line straight through this data going to be a good fit for the data? No, of course not, right? Because this line is a curve. So, but if I ask it to, the computer will draw a straight line. And this happens a lot, right? So a good example of this would be like if I ask students, how many hours did you study for the test and your score on the test, right? That there's some sort of maximal number of hours studying that is beneficial, right? But at some point, the hours studying no longer benefits you on the test. And in fact, could have a negative relationship, right? If you stay up all night studying before a test, you might be so tired that you sleep through the test and you don't do very well, right? So again, it might be a non-linear relationship. Another example would be an omitted variable bias. So in this example, if I put in things that aren't theoretically related. So for example, in a school, I might say, I found a huge relationship between the student's shoe size and their reading level, right, in this elementary school. So does that mean that kids with bigger feet can read better? Does that even make sense? No, of course not, right? It turns out, though, that 5th graders have much bigger feet than kindergartners, right? 5th graders are also on higher reading levels than kindergartners, right? So rather than using shoe size, I left out grade level. Grade level would be a much more explanatory variable for that, right? That's also similar to the example we did before with exercise and school achievement, right? I left out socioeconomic status as an important factor in that relationship. Reverse causality. So it turns out that states who spend more on education experience more economic growth. So this goes back to our kind of correlations not causal, right? But this probably goes actually in the opposite direction. So states who spend more on education probably already experienced economic growth. So if I have economic growth, then I have more money that I can then spend on education. It doesn't work the other way, probably because if I'm spending money on education, theoretically, it would take longer for that money to help spur economic growth, right? So if I'm investing in a 5-year-old, it's going to be, 12 years before that 5-year-old is out in the economic market for me to see benefits to that, right? And then correlation doesn't equal causation. And again, this is so important because we're not doing experimental trials. We're doing regression and correlational analyses, right? Having a higher SAT score doesn't cause you to have a higher verbal score. And I think the classic example here is vaccinations, right? There's a correlation between the onset of autism symptoms and the age at which you get vaccinations, but that doesn't mean that vaccinations cause autism. And that's been proven over and over in the scientific research. And it's really unfortunate that those two things kind of happen at the same time. It's a correlation, but it's not a causation, right? And what we're doing here, and when we're seeing correlations, we're really not saying that anything can cause it. And the problem is that our brains are wired to see causal inferences. We want to make things causal, but they just aren't. Okay. Sometimes if we put too many variables in our equations, they explain out all of the causation. So if I use both grade level and age in an equation predicting height, then neither one of them will look very important. So it'll be like m1x plus m2x1 plus b equals y, right? So I have two slopes. Neither one of those slopes will be very big because they're both explaining part of that height. So grade level and age are basically the same thing for most kids. They would both explain height pretty well. And so neither one would look very important. So we don't want to use this variables that mean the same thing in the equation. So we actually see this a lot in schools because we'll use, let's say, both third and fourth grade scores to predict fifth grade scores, but there's usually not a big difference in scores from year to year. They're kind of explaining the same thing, previous scores. And so a lot of times when we're using more than one grade level scores in our equations, we're actually kind of experiencing this, what we call multicollinearity. So we want to avoid that. We want to avoid using highly correlated explanatory variables in our equations. And then this one's so common. It's called extrapolating beyond the data. It's really saying that I get results in one area and I try to make them fit everywhere, right? So we see this in schools when we say, oh, well, look, I got this finding in this suburban school, so of course it's going to work in our urban schools. Of course it's going to work in a different context. And this is a huge problem when I look in one district, I try to make it apply to a different county, but even within the same county, right? So a couple of semesters ago, I was teaching a graduate class of teachers, and I had a teacher who taught on the west side, and she said, oh, I'm so tired of hearing about everything that they do at Chetts Creek Elementary and how great it is, because what works in Chetts Creek with their parents doesn't work with my parents on the west side. It's a completely different population, right? So, and that makes a lot of sense, right? Sending home a folder to the parents at Chetts Creek who are highly involved, who check their kids' backpacks every night. Well, I mean, I don't, but other parents do, right? Makes a lot of sense for parent communications. But in other populations of parents, you know, if I have a lot of English language learners, if I have a lot of non-native English speakers in my school population, sending home a note written in English isn't going to work, right? So I have to think about other ways to communicate with parents. I have to think about other ways to work with those populations. So just because something works in a suburban area doesn't mean it's going to work in an urban area, and vice versa. Just because something's really effective in an urban area doesn't mean it's going to be effective in a suburban area. So we want to be careful about not extrapolating it beyond the data that we have. Just because it works in one population of students doesn't mean it's going to work in another population. And finally, data mining. If I put in a lot of data, if I put in a lot of variables, something's probably going to look significant, or something's probably going to look like it's correlated with itself. But that doesn't mean it's actually correlated. Maybe it's just by chance it happens to look important. So we want to be careful about putting in too many variables. We only want to put in variables into our regression equation that we think theoretically might make sense. So we think back to the shoe question with the reading scores. Why would I put in shoe size? There's no reason to think that kids with bigger feet can read better, right? I only want to put in variables that I think might be important, like age or socioeconomic status, right? So I want you to take a look at this question really quickly. So here is an example of a correlation graph. Which of the following would be an accurate statement about this graph? So could I say that lack of sleep causes lower test scores? Or can I say that getting more sleep causes lower test scores? Okay, I hope that you said neither one of those is correct, right? Because correlation does not equal causation. This graph does not show that getting sleep or getting lack of sleep causes lower test scores, right? All we can say is that there is either a negative or a positive relationship between getting sleep and test scores, right? It could be that people who get more sleep also have a higher socioeconomic status, and it's really the socioeconomic status that's more important, right? Or that people who get more sleep also have tutors in their house, and that's why they did better, right? So we don't know that getting more sleep is the factor, right? All we know is that those two things are correlated with each other. There's a relationship there, right? And in this graph, we can see that it's a positive correlation. So if you have any more questions, if that practice problem didn't make sense to you, please send me an email. We can set up a tutoring session. I'll be happy to meet with you and explain this further, either face-to-face or through a phone call, okay? Otherwise, I look forward to seeing your work this week. Bye!